All right, so we've had 3 snow days now. We were out last Friday, and then the last 2 days, Tuesday and Wednesday. The district, if you have not heard, has scheduled. We were supposed to be out on Monday, February 19th for a holiday. We are now going to be in class on Monday, February 19th. So that's, a month from now. Also, April 19th was a Friday that we were going to be no school day. So now that Friday will actually be a school day. It won't affect us very much virtually, actually, because we normally only have classes on Friday if your grade's low. So if your grade's not below 70%, it wouldn't affect you at all having Friday count. It's just one less day in the summer. We do have June 3rd now added as a makeup day. So that means we'll have meets on Monday, June 3rd now. Because of the snow days we had. And that's assuming we don't have any more snow days. Because if we have more snow days, that's going to push us farther into June than the 3rd. So that's kind of where we're at right now. Right now, it's only added one summer day, just one summer day added for the snow days we've had. But we are going to have those days in February and April, which we're going to be off. Now they're not going to be off. So let's see. We should have 19 of us. It looks like 15 that we got right now. So we've got 4 people that are still sleeping in from all the snow days. Yeah, come on, guys. You get enough rest during all these snow days. You make it to class. We got a lot to cover today, guys. We're cutting it back. We're only doing one lesson since we had snow days and missed half this week. We're only going to do one lesson today instead of 2. But still, that one lesson's got a lot in it. I'm not sure we would have made 2 if we tried, but we would have tried. All right, let's take a look at what we have. Let's see, 5th hour right here. Going to go to our grade screen to see what we're covering. You noticed I've shifted right now. We were going to do exponential and logarithmic functions because they kind of go together. But we have changed that. The only thing this week is we just have the exponential functions. Just the exponential functions. And I'm going to shift this around. I'm going to look at, see if I can do some of this other stuff. I'm going to take 5.04 out. We won't have that. So we'll just have 2 things next week and 2 the next. So I'll take 5.04 out of there. So we're going to cover 5.01 exponential functions today. And let's see what it shows. A lot of stuff to cover in here. Nice. And a lot of it I'm just going to do on paper and not necessarily go by the lesson, but over there. But we're going to learn how is an exponential function created? How can the properties of exponents help us solve exponential equations? Because we've looked at the property of exponents. And what are some real-world applications for exponential functions? And they are used regularly. So starting on page 2 here of our lesson, let's talk about what an exponential function is. And I'm gonna put this up and we're gonna look at it on paper here. Exponential function. We know what an exponent is. If we have like x to the 3rd power, 3 is an exponent. But this is not an exponential equation. For it to, f of x, here's f of x. An exponential equation has to have the variable as the exponent. See, this is an exponential equation. So we just need to make sure we have that clear when we're going through this. We've got to remember what an exponential equation is. Just because there's an exponent doesn't mean it's an exponential equation unless the exponent is the variable. All right, so let's look at that. What would it look like to be exponential? Let's see. Let's say we've got a table with some values. And x is 1, 2, 3, and 4. And the f of x, or the y, is 2, 4, 8, and 16. All right, so when we look at that, we can look at it. A lot of times we think of slope when we see a table. If we graph this, what would that look like? And the slope would be how much does it go up each time, right? So this goes up plus 2, but then it goes up plus 4, then it goes up plus 8. So this is definitely not a line. right? Because it's changing how much it goes up. But we can look at it a different way. Let's look at that a different way. Let's say, okay, we're not going to talk about adding, because we can see there's a different pattern going on there. Going from 2 to 4, that's multiplying times 2. Going from 4 to 8, that's multiplying times 2. Going from 8 to 16, that's multiplying times 2. So this is very consistent. It's not consistent in how much it adds or subtracts. It's consistent in that it's multiplying by 2 each time. So we could say this is actually an exponential equation because this is consistent. Since this is the same, these are all times 2. This is an exponential equation. So if we want to write this equation, we could say f of x equals 2 to the x, because it's being multiplied by 2 each time. So we can say that's 2 to the x power. Well, does that work? Well, let's look at the first one. The first one would be 2 to the first power if x is 1, because it's 2 to the first power, right? So 2 to the first power is just 2. The second one would be 2 to the second power, where x is 2. Well, 2 squared is 2 times 2. That is 4. When x is 3, 2 to the third power is 2 times 2 times 2. So 2 times 2 is 4 times 2 is 8. 2 to the fourth would be 2 times 2 times 2 times 2, which is 16. So yes, we do see that these numbers do match our table, 2, 4, 8, 16. So this is the exponential equation, f of x equals 2 to the x power. So we see a consistent multiplier when we look at the individual values in there. So how do we solve exponential equations? Since we know what an exponential equation is now, so some of it's pretty simple. If we have a very simple one, like 3 to the x equals 3 to the fifth, and we need to solve that for x equals. Well, that one's pretty simple, right? 3 to the x equals 3 to the fifth. Well, x has to be 5. That's the only way that these would be equal. So we can see that's real easy. If we have the same base, which we do, base 3, we can just take these exponents and set them equal to one another. X equals 5. And that's easy to see. But what about when it's like this? 3 to the x equals 243. Well, that's not so easy, right? We're like, okay, I have no idea what x equals now. Well, we have to rewrite it. If we can rewrite this where they have the same base, what is 343? Well, it's 3 times 3 times 3 times 3 times 3. Look, 243. If we take 3 5 times, so that is equal to 3 to the fifth. So x equals 5. But this is hard to see. This is easy to see. So we have to try to get these in the same base number to solve them. Because if we have it where they're both 3s, it's easy to tell what that is. So in solving these, we need to review a little bit on our rules for exponents. So we had the power. Let's start with the product rule. Product rule is easiest, as we review here. Product. So rules. We're going over the rules. And this works for exponential equations the same as it does for just the regular equation that have exponents. When we talk about the exponent rules for product, if we have x to the third being multiplied by x squared, we know we can just take the 3 plus the 2, and that is x to the fifth. So the product is when you multiply two exponents together. And they have to have the same base. They're both base x. So when we multiply two exponents, we can just add those, 3 plus 2, and it's x to the fifth. And we know that's true because x times x times x is x to the third. And if we multiply that times x, that's just 5 x's being multiplied together, and that's x to the fifth. So that's the product rule. Let's look at the quotient rule. That's when we are taking like x to the fifth divided by x to the third. Quotient means what happens when you divide. Well, our rules for quotients, if you remember, means we can just subtract those. It's x squared. And again, we can prove that to ourselves by saying x to the fifth divided by x to the third. Let's see, these cancel each other out. Those cancel each other out because x divided by x is 1. X divided by x is 1. X divided by x is 1. So it's just x times 1 times 1 times 1, or x squared. So yeah, we can just subtract when we have the same base. Again, they both have to have the same base, which in this case is x's. Let's see, then we have the power rule. And that's when you have, let's see, x to the third taken to the fourth power. See, I have an exponent taken to an exponent. And for that, it's you multiply them 3 times 4, or x to the 12th power. You just multiply them if it's a power to a power, because this is x to the third times x to the third times x to the third times x to the third. So we end up with 12 x's, x to the 12th. And then the last one we need to remind ourselves is when you have a negative exponent. So if you have, let's see, I'm going to do x to the negative 2y to the third. That is the same as y to the third divided by x squared. If it's a negative, you can move it underneath the fraction, and it makes it a positive. Or it works the other way. If we have 1 over x squared y to the negative fourth, we can move the y on top. We leave the x on bottom because it's already a positive exponent. But anytime you have a negative exponent, you can either move it on top of the fraction or move it below the fraction to make it a positive, because we don't want to write our final answer should not have a negative exponent. We need to make it a positive exponent, and that's by moving it above or below the denominator, the numerator or denominator, just depending on what it starts at. This is technically all over 1. Anytime you have a number, it's over 1. So we can move the x squared to the bottom like that and make that. So that's our exponent rules that we just need to keep in mind, because these work even with exponentials. Even if the x is the exponent instead of the base, these rules still apply, because these are just how they work anytime you have an exponent, regardless whether exponent is a number or a variable. All right, so we're going to look at, this lesson, you can go back and look at all of it. I'm doing a lot of this on paper just to go through these things. They go through a lot of the same things. But we're going to look at how to solve an exponential equation when we have a different base. Like this one has 1 over 256 equals 16 to the x minus 9. I said we need to get them to the same base. Here, let me do a simple one first before they look at that one there. So if we have, let's say, 2 to the x. Like I say, a very simple one here. Equals 8 to the x minus 1. All right, we're gonna solve this. I don't even know what the answer is. I just made this up. In order to set these equal to each other, like, we could set x equals 5 because these are the same base. We have to get these the same base, which right now they're not. But we know 8 is a power of 2. So we could rewrite this as 2 to the x equals 8 is 2 to the third power, right? 2 times 2 times 2 is 8. And that would be taken to the power of x minus 1. That's still 8 to the power of x minus 1. Okay, so using our power rule, we have a power to a power. Now we can rewrite it as 2 to the x equals 2 to the, and I can multiply these. 3x minus 3. All right. Now I've got, what have I got? I got the same base. They're both base 2. So to solve that, I can just take their exponents. X equals 3x minus 3. Just take those, and I can solve that. Subtract 2x. Oh, 3x. Sorry, subtract 3x. So I've got negative 2x equals negative 3. Divide by negative 2. X equals 3 halves. So when I substitute 3 halves in for x here, those will become equal to each other. We can test that. Let's see. 2 to the 3 halves power, which we know is the cubed root of 4, right? 2 squared. But let's just leave it in this fraction form for now, which would be 8 to the 3 halves minus 1. 2 to the 3 halves equals 3 halves minus 1 is just 1 half. Right? Because it's 3 halves equals 202. So are these equal? 2 to 3 is 8 to 1 half. If we rewrite this as a 2, 2 to the 3 halves equals 2 to the third to the 1 half, and multiply those together, 3 times a half is 3 halves. So this is 2 to 3 halves equals 2 to 3 halves. So it did test out when we substituted it back in there that it equaled the other side. But let's look at the example they want to do here. All right, here we are. It's just 2 minutes and 8 seconds.
First, create equal bases. Before solving for the variable, the bases of each exponential expression in the equation must be identical. Rewrite the numbers 256 and 16 with a base of 4 and exponents 4 and 2, respectively. According to the properties of exponents, when the denominator of a fraction contains an exponent, such as 1 over 4 to the 4th power, you can rewrite the expression with a negative exponent. On the right side of the equal sign, there is a power raised to a power. By the power of a power property, these exponents will be multiplied. Be sure to distribute . Now, solve for the variable. Once the bases are identical, eliminate both bases and find the value of the variable. Now, check your work. Substitute the value of the variable into the original equation to confirm the solution. The solution x equals 7 is correct.
Yeah, we can see right there at the end they had
Equals 7 is correct.
That's 1 over 16 squared, because 16 to the negative 2, remember we can move that underneath the fraction. 1 over 16 squared, and then 1 over 16 squared is 1 over 256. So there's how they solve that. Let's look at a different example right here. Oh, this is a good one. Let's do this on paper. So this is the square root of 11 times 12x. 121 to the x plus 1. So let's try to get these to the same base. Right now, we've got two very different looking numbers. We have a square root of an 11 and we have a 121. Now we remember we can write the square root as an exponent. We did that a while back. 11 to the 1/2 power is the same as the square root of 11. So we rewrite that and we're still taking that to the power of 12x. Okay, so that's rewriting this to has a base of 11. And 121 is 11 squared. And that is still being taken to a power of x plus 1. So we've got base of 11 on both sides. Let's simplify these because remember our power to a power rule says we can multiply that. So 11, 1/2 times 12x is 6x, right? 12 divided by 2. On the other side, we've got 11 to the multiply 2 times x plus 1, which would be 2x plus 2 when you distribute. Because remember, you got to take it times both, the x and the 1. So now we have the same base. Base 11. And when you have the same base, you can drop the base and just set the exponents equal to one another. So now what started off looking really nasty is coming down to some pretty simple algebra. 4x equals 2. X equals 1/2. So x equals 1/2 was our answer. So in this equation, if we substituted square root of 11 to the power of 12 times 1/2, it would equal 121 1/2 plus 1. If we simplify all of this, this again is 11 to the 1/2 power, and 12 times half is 6. And then power to a power, so this is 11 to the 3rd power. All right. Over here, we've got 11 squared to the power of 1/2 plus 1. And if we simplify that, 2 times 1/2 plus 1. 2 times 1/2 is 1. 2 times 2 is 2. 1 plus 2. They equal each other. It's 11 to the 3rd power, which we could do that in math if we want to multiply it. And it's like 1,331 or something like that. But it'd be the same on both sides. This proves this the same on both sides. We checked our work. It checks out. So x equals 1/2. So, all right. So let's talk about real world applications of this, because it is actually used a lot. There's exponential growth. If we went back and said, oh, here's a good example. Okay, let's talk about this. Let's say you had a very rich uncle that came to you with an offer. He says, okay, let's say you just got out of school. It's June. He says, all right, you want to make some money this summer? I will give you money this summer. June has 30 days. So I'll tell you what, I'll give you every day, I'll give you $100 for the month of June. You just come work for an hour in my garden. Or I'll tell you what, I'll make you a different deal. If you want to work for an hour in my garden, I'll just give you a penny on June 1st. And on June 2nd, I'll give you 2 pennies. and I'll give you 4. Every day, I'll just double how much I'm giving you for the month of June. So your choice. I can give you $100 a day, or I'll just give you a penny on the first day and double it every day. And at the end of June, you walk away with your money. Which one are you going to do? Like, well, $100 on June 1st. I could do something really good with that right off the bat. Every day I'm making $100 to work an hour. Or, all right, I'm going to go make a penny on the first day, and I'm going to make 2 pennies, and I'm going to make 4 pennies and 8 pennies. I ain't going to be able to buy a hamburger for a couple of weeks. How do you know which is better? How can you figure that out? Wow. Well, I don't know. What are you taking? Put it in the chat. Which way are you going? You going to take $100 or you going to take a penny? June 1st, what are you taking? Which deal are you making with your very rich uncle? Jonathan says you'll get more at the penny. Ty says, yeah, you get like $5 million with the penny. You're not making 120 by the 5th day, Jonathan, because you get a penny, then you get 2 pennies, then you get 4 pennies, you get 8 pennies. By the 5th day, you've got 16 pennies that you're making that day. So I'll take the pennies and multiply, be more than $100 a day. Esteban says, I'll take $100 and we'll flip it and we'll do some work. So, well, let's do some math and see what we can find. How much would we have at the end of June in both scenarios here? Let's see. Well, we know if we get $100, we're just going to take that times 30. Because we're going to get that 30 times. So we're going to end up with $3,000. That's our total. Right. So that's our total. If we start out with a penny, we can use this formula. F of x equals, that's how we get to start. And every day it's going to double. And we'll do it as an x. That's an exponential equation. So like on day 1, when x equals 1, first day, you got 1 penny. Oh, let's see. Is that x or is that x? That's actually x minus 1. X minus 1. I got that wrong. It's going to be 1 penny times 2 to the x minus 1 to the 0 power. Because x is 1. 1 minus 1 is 0. 2 to the 0 power is just 1. Anything to the 0 power is 1. So a penny times 1. A penny times 1 is just a penny. That's what you get day 1. 1 penny. On day 2, x equals 2. You get 0.01 times 2 squared. Oh, I'm sorry. To the first power, because it's 2 minus 1. To the first power is 2, so you get 2 cents. On the third day, you got 0.01 times 2 squared, because we're subtracting 1. So that's 4 times a penny, 0.04. So we know how this works. So let's look at day 30. When x equals 30. So you got 0.01 times 2, and we've multiplied it times 2 29 times now. So we're going to need a calculator since we didn't figure every day. All right, so 0.01 times 2 raised to the power of 29. It's doubled 29 times. That is going to be $5 million. $368,709.12. That's what you get on day 30. You get $5 million on day 30 by starting out very humbly, starting with a penny, then 2 pennies and 4 pennies. And you can write it all out. You can write this out 30 times, doubling it, and that's what you'll get to on day 30. So, yay, rich uncle. I will be humble and start out not making hardly any money for the first couple of weeks. There's a chart in our lesson. Let's see. Is that the next page? Where'd they put that chart? that details out how much you get all $30, all 30 days. Here's the $100 every day. We know that's $3,000. Here is a doubled every day. Look at 7 days, you're still just making 64 cents. After 2 weeks, you finally made 81 bucks. You're almost to the $100 a day. The first 2 weeks, you're not hardly making anything. But then when that starts doubling, 163, 327, 655, $1,300, $2,600, over $5,000, $10,000, $20,000, all the way up until the last day. So the total, if you added all 30 days together, is actually 10 million bucks that you made for the whole month. 10 million. That's exponential growth, guys. Exponential. This is just adding. This is just arithmetic. This is exponents. That's why you should start a 401k or a Roth IRA in your 20s, because it can exponentially grow throughout your lifetime. If you have a good investment guy, it should double every 8 years. And so you want it to double as many times as possible. So start putting money away in retirement young. Don't wait till you're 40 or 50. Start in your 20s or teens if you got a job, because it can grow and grow and grow. All right, so here's that exponential growth formula, and this is if just with the T. So if we want to know our total amount, see, this told us how much each day. If we want to know our total amount, we don't do the x minus 1. We just do the, well, we can do T for time, 0.01 times 2 to the T, and that would tell us the total, which would be one more doubling, and that's where the 10 million total came from, 10,700,000, etc., whatever. That'll tell us in 30 days how much money would we have. $10 million. Very nice stuff. So there's some formulas we need to know for compound interest. Let's talk about at a bank. Compound interest. That is a day-to-day, everyday exponential formula. So this is good to have in your notes. If I want to know how much money I can make in the bank with an investment, here is our formula. You're like, whoa, that's a lot of variables. Yeah, there's only one number and it's a 1. So P is your principal. And that's a PLE principal, not a PAL principal. We're not talking about Mrs. Scott. Miss Scott, we're talking about starting amount, principal. Start. So you're starting dollars. The R is the rate of interest. And that's a decimal. And see the N. Number of times calculated per year. Number of times calculated per year. And then T, years. All right, that is our basic formula, and now we're going to use it and show you how that works. All right, let's say we've got a bank account, and we're going to put $10,000 in it. All right, so the amount of money we will have, we'll start with 10,000. And let's say what kind of interest you're going to make. Let's say we're going to make 8% interest. All right, it's some kind of special account we got that we're making 8% on it per year. And they're going to give us interest monthly. Monthly. So 8% as a decimal is 0.08. If you multiply something times 0.08, that adds 8%. And monthly means we're going to do this 12 times a year. And then NT, 12. And we want to know how much money we'll have after 10 years. So 12 times 10. So that's just taking these numbers and plugging them in. We start with $10,000. We're going to make 8%, 0.08. Remember, it has to be a decimal. N is the number of times calculated per year. So if it's monthly, we're dividing it by 12, and then we're also multiplying it by 12 up here for the N. And then T is the years. So we said after 10 years, how much money will we have if we put it somewhere where it's going to make 8% interest, and they're going to give us the 8% every month, our interest every month. So let's do this math then. A equals 10,000. 1 plus 0.08 divided by 12. Well, let's pull out our calculator again for that. 1 plus 0.08 divided by 12. 1 plus, and I'm going to put this in parentheses, 0.08 divided by 12, close parentheses, equals. All right, so that number is 1.06. We'll go to like 3 sixes. Oh, then we'll round that up to a 7 because it'll go for it. Oh, I should have 2 zeros. Oh, 2 zeros. 100. 6, 6, 7. All right, and then 12 times 10 is 120. All right, because that's how many months we're going. 120 months. 10 years is 120 months, and this is how much we're getting every month. Every month we're getting 0.00667 interest added on top of that. But it's going to grow exponentially because the first month we're going to get a little bit of interest, but then the second month we're getting interest on that interest. And then each month after that, it just keeps growing. So let's see how much our 10,000 turns into. All right, 10,000 times parentheses 1.00667 raised to the power of 120. We will have $22,205.22. That's how we use that formula. We have to put in the principal, the rate of interest, the number of times calculated per year, and the number of years into this. Let me highlight this because this is great for your notes. And that will tell us the amount of money we would have after 10 years. That's not adding any more money. That's not taking any money out of the account. That's just letting it grow exponentially. Letting it grow exponentially. You can turn it $10,000 into $22,205. So in your average retirement account, if you have a good investment guy, he should make at least 8% month average. Some months you're not going to make any money because the stock market goes down, but other months you're going to make 20% because the stock market is going to jump up. So on average, if you make 8% a year, if you put $10,000 in retirement, 10 years from now, it should be more than double. Like I say, usually it doubles about every 8 years if you got a good investment guy knows what he's doing. So in 10 years, it'll more than double. So see, if you put $10,000 in retirement in your 20s, in your 10 years later, you should have 22, and then it should grow and grow and grow. Exponential compound interest. This is compound interest. So let's see. There's another thing that's really kind of theoretical. Talking about interest is amount equals PERT. I like that, PERT. This is compounded continuously. What does that mean, compounded continuously? That means I'm going to give you interest every second. Every second, I'm going to give you the interest you're owed for this 1 second. Okay, so that doesn't make any sense money-wise. That doesn't happen. But if we're talking about in the science, let's talk about in a science lab or something, and you are growing bacteria because you're making some kind of pharmaceutical product, right? You're making some kind of medicine that uses this bacteria that grows. And if the bacteria grows exponentially, like it'll start, let's say it doubles every day, and it doubles and doubles, and it's constantly always in the state of doubling. It's not like it's just every once in a while. It's in a constant state. So it's compounding continuously. Everything's growing constantly. This is the formula used, and the P is still the starting amount. The rate R is the rate of growth. Again, it's a decimal. And T is time, usually in years or whatever it is. So you're like, what's E? E's a number. You're like, what? No, it's not a variable. E is actually a number. What is E equal to? Well, let's go to our calculator. See that E button? Our calculator has an E button right there. Because E is a number. It's like pi. Pi is a number. E is a number in mathematics. E. Well, what's it equal to? Let's click and see what E equals. There's what E is. In mathematics, E equals 2.71828. Let's see. 1828 again. And then 459045. It goes on and on and on. It's like pi, it doesn't end. E is a number. E is a number. So to compound continuously, we use this formula. Now let's use that. Let's say we start with a certain amount of bacteria. We start with 100 bacteria. So P equals 100. Its growth rate, let's say it grows at 10%, 0.1, 0.1 is 10%. And we're going to check it after 2 years. No, let's say 8 years, something like that. So what amount will we have of this bacteria if we start with 100 and multiply it times E to the 0.10 times 8? So that's A equals 100 to the E 0.8. Since 0.1 times 8 is 0.8, let's see how much it grows. If it just grows 10% per year, and it's 0.8. Or it's per day or per month or whatever period we're looking at. So let's see, 100 times, parentheses, E raised to the power of 0.8. We'll have 222. 0.55, which means we really won't have more than 222 because we can't have a part of a bacteria. So we really have 222 bacteria at a growth rate of 10%. Now, if it's doubling and that becomes a 2, it grows a lot faster, right? Maybe the rate is 2. It doubles every year or something. But that's how you use compounded continuously. But that's usually only in like science and stuff because money does not compound continuously. The formula need for money is this right here. And you will have to use that in the assignment this week. You have to know how to plug these numbers in. All right. There's another one we need to look at, and it's decay. This one you will understand as well. For decay, the amount over time is equal to our textbook uses L. I don't like using L because it looks like it could be a 1 or something if you write it wrong. But I'm going to use it just because our textbook uses it. 1 minus the rate over time. And again, there's also continuously, where you can use the LERT. Right. You can do the same thing with decay. But anyway, that's if this is used like in medical, like if they give you a shot of medicine, you're in the hospital, they give you an IV, they can use this decay formula to figure out how much of it's still left in your system after 6 hours. They can see how fast it leaves your body after 6 hours and use this LERT. That's when that's used. But let's talk about this decay. This is to say, okay, you buy a car and you go out and get a brand new car and spend $40,000. Now, the one thing we know about cars is they're going to lose value. Cars don't go up in value until they get old. After many, many years, cars stop losing value and start gaining value as they become antiques. But for the first many, many years, there's 20 years at least, you're going to lose money on a car. And let's assume that you're losing 20% of your value every year. That would be on average, because like the first year, you're going to lose like 30 or 40% of your value. That $40,000 car a year from now is probably worth $28,000. It ain't worth much. I mean, compared to how much you're spending on it. And let's say, how much is this $40,000 car worth after 5 years? Now, this is a real world problem. You'll have some of this that you'll have to do in our assignment, but let's look at this. All right, let's use our formula. Negative 20%. Remember, we need that as a decimal. So that's going to be negative 0.2. 0.2 is 20%. Just divide 20 by 100. Anytime, if you need to know how to convert percent to decimal, divide by 100. So 20% divided by 100 is 0.2. So that's how you convert percent to decimal. So you might have that in your notes if you're not comfortable doing that, if you're not real good at that already. But let's go back to this formula now and see what we got. So the amount after 5 years is going to be L is going to be our starting amount. That's how much we spent on the car. So it was worth $40,000 when we bought it. 1 minus the rate. The rate is 20%. Well, 20% loss, so it's 0.2 to the 5. We don't have to make that 20% loss. The rate of decay is 20%. 20% decay. 1 minus 0.2. So after 5 years, it's going to be worth 40,000. 1 minus 0.2 is 0.8 to the 5th power. Let's see how much that $40,000 car is worth after 5 years. And you start out, if you finance it, you spend $40,000 on it plus interest, because every year they're going to be doing compound interest on you. So you're paying more than $40,000. You're going to pay $50,000. And meanwhile, your car is going down in value. Let's see how much your car is worth. 40,000 times 0.8 raised to the 5th power. Your car is going to be worth, at the end of 5 years, $13,170.20. And that's probably pretty accurate. And if you go to the dealership to trade that in 5 years, they're not even going to offer you that. They'll give you $4,000 probably, and then they'll sell it for $13,000. So cars go down a lot. Cars are a terrible, terrible investment. If you buy a brand new car, you must really, really like to spend money, and you better really, 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 really like that car, because it's going to cost you a lot of money. Because this is pretty accurate. $40,000 car, probably worth $13,000. I bought a 6-year-old car a few months ago that sold. It was like $38,000, and I paid $15,000 for it. The person that traded into the dealer got a lot less than 15 for it. They got like 6 or 7. So they spent $38,000 and they got like $7,000 for it when they traded it in after 6 years. So this isn't off by much. But this is the decay formula. So this is good for your notes right here as well. But the thing is practicing, learning to convert percent to decimal, because you have to have this in a decimal form. Have to have it in the decimal form. Let's see if there's anything else in our lesson that we're missing. We need to have those examples. So there's the exponential growth with the money. Let's see, $100 invested at 5% per year, compounded quarterly. So that's 4 times per year. 4 times a year. How much would be worth at the end of 2 years? Let's watch one of their examples just to know that. Let's watch one of theirs. I got to share it differently again because of the sound. All right, here we go. All right, let's watch one of their examples so we can get another view of this. I had $100 invested at 5% per year, compounded quarterly, so that's 4 times per year. Let's see what it's worth in 2 years. Get that started here. 2 minutes.
If $100 is invested at an interest rate of 5% per year, compounded quarterly, how much will the investment be worth at the end of 2 years? To answer this question, first use the scenario to define each variable. The principal, P, is $100. The interest rate on the account is 5%, which is written as the decimal 5/100ths. The account is compounded quarterly, which means 4 times each year. Therefore, N is 4. The question asks you to find the account value after 2 years. So, T equals 2. Now that only one variable is left, use the order of operations to solve for that variable. When working with money, round the solution to the nearest cent, or nearest hundredths. So, after 2 years at a 5% interest rate, compounded quarterly, the initial $100 investment will be worth about $110.45.
Yeah, so you got 5% per year, which would normally just be $5 for the first year, $5 for the second year. But you had also in that, your interest was gaining interest. After your first quarter and you got some interest, now you get paid interest on that interest. And that's where your extra 45 cents come in, is that you're getting interest on interest. Now, this is just 5% in just 2 years. So it didn't make a whole lot of money, but it's still free money that you made just off interest on there. Let's see. There's one, $500, 6%, compounded continuously, which I can say that's like every millisecond they're giving you your interest. That's not going to happen. But after 3 years, we'll see it makes a lot more money because of the compounded continuously. $598. It made almost $100 in just 3 years because it's compounded continuously using that E. Hi, Bella. Hi, Haley. So, all right. The lesson summary here. Oh, here's exponential decay functions. Talks about your car depreciating 20% a year. This is if a new car is purchased for $15,000. You can't buy a new car for $15,000. So their example is very outdated. And after 5 years, it's worth less than 5. Ours was a little more realistic with a $40,000 car, just because the numbers. So, example 2. This is medicine. It's using that ERT instead of the other formula. So if you have 250 milligrams of a drug and it leaves your bloodstream at 5% per hour, after 8 hours, how much of that medicine is still in your bloodstream? So they calculate that, and it's down to 167 milligrams. So that's calculations they do in the I said doo-doo. That they do use in the medicine field, pharmacists and nurses, doctors, etc. Let's see, this is using a golf tournament. So lots of examples there, but here's the lesson summary. I think my box is kind of messing up. It doesn't look real clean and neat there, but all right, here's the lesson summary. You can print this and put it in your notes if you want, but it talks about the exponential functions. Create equal bases on both sides so you can eliminate the base and just solve for the variable. Exponential growth, exponential decay, and here's the formulas for those. A equals P, 1 plus R over N, raised to the power of NT, and the E right there. So I think that's having trouble loading correctly because that page looks kind of funny. I'm just reloading that to see if it looks different when it reloads. There, that looks more normal. It just didn't load properly. But yeah, there's the formula for compound interest, and there's continuous interest right there. And then the decay one you have as well as I gave you. So, all right, let's look at our assignment right here. I'll change this. Says you have one attempt. I will change that to make sure you have more than one attempt. If you do it the first time and mess something up, I want you to be able to redo that. So I'll go back and change that. Here's one that gives you the same base. That's nice. It gives you a 3 on both sides. So x plus 6 equals 4. Solve that. Here's one where they give you an 8 equals 2 to the power of. So you're going to have to change that 8 to be a base 2, which would be 2 to the third power. We know that. Here's where you got to change both sides. This is an 81 and a 27. Those are both a power of 3. So you can change those to 3 to a power, 3 to a power. 1 over 36. So that is a base 6. They left the other side base 6. And then they give you one with a square root 6. Now we have the compound interest. They even gave you the formula right here. So if you didn't have it in your notes, they gave you the numbers, the 240, the 9%, and the 14 years. They give you another one here. Here's a bacteria. How much bacteria? This uses the ERT, P-E-R-T. That's the one that uses the E. Here's a depreciation. So that's the decay formula. And then here's the decay formula using the E. So there's your 10 problems. Like I said, I will go back and make sure you have more than one attempt on there. It says you can only try it once. I'll fix that where you can try it more than once. But otherwise, that's it. We're just going to do this one lesson this week. Just that one assignment this week. And then next week, we'll look at the rest of the stuff on there. So, all right, guys. Hope you're able to stay warm during all of the very, very frigid cold weather we had. Maybe you got out and made a snowman, had a little fun in all this cold weather, but you really had to bundle up because, as I told my wife when we left the house this weekend, I said, if you want to keep it, you better cover it up. So, anything hanging out is going to get frozen off. All right, guys, I'll let you go. We will see you on Tuesday, and we'll have a normal week next week, hopefully. I don't think there's any more snow coming in. Besides, we don't want to be here 4th of July or nothing. We don't need a whole lot of snow days, but we'd like to have a little fun with it. All right, guys, got any questions, email me. Otherwise, I'll see you next week.